Hi everybody, Cal here. Today we're going to talk about sections 4.3, linearly independent sets and bases, and 4.4 on coordinates. Section 4.3 may be the most important section remaining in the course. The idea of basis is going to be super fundamental to everything else we're doing. So the book starts by redefining linear independence, dependence. This is old stuff. It's being redefined here because we've only seen it in the context of vectors in Rn before. Here it's general vectors. No real difference. I would not spend a lot of mental energy right there. Theorem 4 here should seem really similar to Theorem 7 in Chapter 1, which I said at the time was key to your understanding of linear independence. No different here. The paragraph at the bottom here talks about the difference between linear dependence in Rn and in general vector spaces, which, not a big difference. And we have a couple of examples of vectors that are not in Rn being dependent or independent. And these are interesting examples. I would at least think about them for a few minutes. Then we get to our big definition for the section, the definition of a basis. The language here is terrible. A basis is a linearly independent set that spans your subspace. Okay, a basis for a subspace is a linearly independent set that spans that subspace. Don't worry about this horse crap about the subspace spanned by B coincides with H. Come on, just the equation will do. Alright. Examples 3 and 4 and 5 and 6 all look at finding bases for certain subspaces. And some of these are important. I would spend your time here, especially example 4 introduces a word, standard basis for Rn. Example 6 talks about standard basis for Pn, the nth degree polynomials. Alright, over here on 212 we have the spanning set theorem. The spanning set theorem is an important theorem. It is not the answer to all of life's problems, but it is an important theorem. Make sure you understand what the spanning set theorem is saying. It says that if I have a spanning set for a subspace, some subset of that spanning set is a basis for that subspace, assuming the set wasn't empty in the first place. Alright. Then we get into finding bases for the null space of a matrix and the column space of a matrix. And this is going to be extraordinarily important to what we're doing. Make sure you follow through example 8 and example 9. Theorem 6 distills what those are doing. Remember that the pivot columns of a matrix A form a basis for the column space of A. That means you might need to row reduce to figure out where those pivots are, but you're going to take those columns from the original matrix A. And that's the content of this warning down here. It's an important warning. We already know how to find a basis for the null space of a matrix. We learned it in section 4.2. That was a linearly independent spanning set that we found by finding the vectors in parametric vector form, as you may recall. This section here, called Two Views of a Basis, is pretty important. I would spend the time to understand what it's saying, and I would read the corresponding example. Okay? Moving onward to section 4.4, Coordinate Systems. Here we're going to kind of tie together a lot of the things we've been doing about vector spaces and subspaces, and this is going to let us get at why they're important. We start off with the unique representation theorem, which is a really important consequence of the concept of a basis. Do read it. Do read the proof. It's pretty important. And here we define the coordinates of a vector relative to a given basis. Make sure you understand what this definition is saying, and I would read everything going after it pretty carefully. Introduces a lot of concepts pretty quickly. Go through the examples where it's talking about how to find the coordinate vector of a particular vector. The graphical interpretation of coordinates is pretty important. I would see what you can get from that section and from the example 3. And it will talk in general about coordinates in Rn. I would, again, just be working through these examples. This stuff is pretty important. It talks about a change of coordinates matrix, which is sometimes useful here at the bottom of 228 and the top of, bottom 220, top of 221. Talks about the change of coordinates matrix and why that's important. The coordinate mapping might be a little bit of a formal section for some. There's still valuable stuff in here. We're not going to do a heck of a lot with it. So, again, this is like for the mathematicians in the audience. The concept of isomorphism, however, in the middle of 222, it's going to be pretty important, if nothing else, for a geometric understanding of why coordinates are cool. Example 5 also lets us get at why coordinates are cool. Here we have a problem that's posed about polynomials, and coordinates let us turn these into a problem about vectors in Rn, the way we're used to. There's some power to that. Examples 6 and 7 are worth working through. And that kind of ties up this section. So, there you go.